Hey, how's it going? Hey,
I just want to ask you, like we have a we're doing CATIA as a like one of our subject, and I want to know how is the finite element analysis different than that compared to ANSYS?
yeah, it's a good question. I actually don't have that much experience with the CATIA at all. I've seen someone use it a couple times, but in theory, if you're doing something like relatively simple, like you're just applying loads, and like basically the stuff we covered so far in the class, I think it'll do just
So
fine.
the project for us is like do something I'm not taught in class.
Yeah.
So in that class, he's not taught as FEA, so we'll do FEA.
Yeah.
That has an option. So I wanted to know, like, if you knew how it works. Is it pretty similar to what we do in class? Or?
I mean, the way you set it up is going to be different because the interface is going to be different.
So we first design and then based on that, we just have to.
In terms of accuracy, I mean, if you're doing some fairly simple stuff, just like fixed supports and forces and pressures, it should give you pretty accurate answers.
Okay.
Usually, the big differences in these softwares, first of all, is the user interface, how you even set up a mesh. And then the other difference is kind of more on some of the more advanced features. If you're doing something, fairly basic, I would trust it just.
No, is it okay if you could just check it out if we do it and just like if I send you a draft of how I've done it? Could you just check it out if it's not?
Yeah, I could probably check it out. I mean, I don't have CATIA.
No, what I'll do is I'll do it, take screenshots and put up in Word and send that to you.
Okay. Yeah, I can take a look at that.
Cool.
Yeah. Mm-hmm.
Hello, Dr. Chan. Can you hear me?
Yep, I can hear you.
Sounds good.
Oh, nice.
So this guy asked me a question.
Dr. Chan,
Yes.
I have a quick question.
Sure.
Can I ask it?
Sure, of course.
I'm trying to see how I could word this. So I know that FEA can be applicable to static situations and dynamic situations.
Yep.
Which one is it more popular in? Which is FEA used more for static applications, or is FEA used more for dynamic applications? I know it could be used for both, but I'm wondering if it's used. I know that structural and civil engineers use FEA heavily, but I'm not quite sure for other types of engineers other than mechanical. I'm assuming because of this graduate program.
Yeah, I mean, it depends on just what your application field is. So if you're designing static structures, I mean, you're going to use the static.
Mhm.
But if you're designing dynamic systems, then it's on that. And so it's not really like a one is better than the other, because it works for
I
both.
see.
It just depends on just what you're working, because yeah, it depends on your application more so than anything.
I see. Sounds good, sir. I feel like I'm just trying to generalize it too much when it really depends on the situation.
Sure. Yes. Yeah. Mhm.
Sounds good, sir.
All right, it's 7 o'clock. Let's go ahead and get started. All right, good evening, everyone. How's everyone doing today? Doing good. All right, so we have an ANSYS activity today. So it's been a while since we had one. And so this is the activity that I had originally planned for before spring break, but now it's after spring break. So now that the midterm project's done, so we can start doing ANSYS activities again. Okay. So we do have a little bit of an accelerated schedule for the last few weeks. So we have after this week, we have 5 more weeks. And we have 4 more activities to go through. And so, we are going to be doing a lot more activities. So it is kind of a lot more activity reports, yes, but, I think this is kind of a more exciting part of the class because we're getting into more, I would say, more advanced features in ANSYS that, it's usually not covered in a lot of basic classes. And so, this is going to be fun. Okay. All right. So I did, even though we're not going to talk about the final project together until Monday, I did post the specifications for the final project. And so if you were curious and you wanted to kind of take a look before Monday, it should be up on Canvas. And so there should be a new assignment there under final projects called final project. And from there, you can read kind of the instructions, kind of the rubric, the template, and all that stuff. Okay. You should see that it is, basically similar to the midterm project, just with some added kind of requirements based on what we're going to learn in the second half of the course. Okay. But we'll go over it together on Monday. And so, you can kind of wait until then. And I'm giving you over a month to work on it. So the due date for the final project is going to be May 22nd. And so, right now we're kind of in the beginning of April. And so you have about 6 weeks to do the final project. Okay. Okay. And so with that, let's get on to the activity today. So the activity today.
Can I ask a question, sir?
Oh, of course. Yes. So
you mentioned there's 4 assignments. Is that so there's assignment 5, assignment 6, assignment 7. Is that 4th assignment the final assignment, or are we going to be doing assignment 8 also?
So it's so activity. So there's 4 more ANSYS activities. So it goes up to
and then the final.
The final project is separate from.
Okay, sounds good. I was just making sure.
Yeah, oh, for sure. Okay, so the activity today, just like what we talked about on Monday, is going to be on dynamics. Okay, and what we're going to be simulating is a car crash. So the CAD file that I gave you guys has a chassis of a car. So I took the wheels and the engine off just because they're not really needed for this. And we're basically just going to ram it against a wall and we're going to see what happens. Okay. So this is a great situation for dynamics because this is something that you can't really simulate in statics. Because there's a lot of kind of vibration, there's a lot of kind of dynamic response here that's not possible in statics, and so I picked this kind of for that reason. Okay. And we're going to be using the tool in ANSYS called explicit dynamics, because it is something that happens on a very short time scale. So those types of situations are great for explicit dynamics. Okay. All right, and so if you haven't already, I would open up ANSYS Workbench because as you know, it takes a few minutes to open that up, and then you can also download the CAD file on Canvas as well, which should be this car crash analysis.igs. Okay, so it's all within that activity 5. Okay. Okay, and so before we get started on the activity today, are there any questions I can answer? Okay, all right, so let's go ahead and get started. So let's go ahead and open up Workbench here. Okay. And what we're going to do is we're going to make use of this explicit dynamics. And usually when we're at this point right here, we use our static structural module, but instead we're going to use explicit dynamics. And so from the toolbox here, you're going to take explicit dynamics and you're going to click and drag it over to this area over here. Okay. And just like we normally do, we're going to import our geometry. So you're going to right click on geometry here. And you're going to import your car crash analysis.igs. Okay. And it should import just fine. Okay. All right. And so, but before we jump into mechanical here, we have to add some material properties. So let's go ahead and double click on engineering data. And what we're going to do is we're going to add aluminum alloy, right? So we're going to click on engineering data sources. Okay. We're going to go to general materials. I can find it. This mouse is being annoying. General. Here it is, general materials. Okay. And so under general materials, we're going to look for aluminum alloy and we're going to add that to our project. Okay, so you're going to click on this plus arrow next to aluminum alloy, and you should see the book next to it. Okay. And so when we click on outside of this, you should have two materials in our project. So you should have structural steel and you should have aluminum alloy. Okay. All right. Any questions on this so far?
Yeah, Professor, I have a quick question.
Yes.
What was the analysis system called again?
Explicit dynamics.
Thank you.
Yep.
Engineering data source that which.
Oh, it's under general materials. Yeah. Mm-hmm. Yeah, it might be in other categories, but I typically find it under general materials. Yeah. All right. Any other questions on this up to this part right here? Okay. All right. So let's go ahead and close this out. And then let's go ahead and open up ANSYS Mechanical here. So let's double click on model. And so this is going to open up ANSYS Mechanical. Okay. All right, and so if you open up ANSYS Mechanical, you should see two parts to your system. So we have a wall and we have the car. Okay. And if you click on geometry here, you should see that there are two parts. So we have part one. Part one is the car. Part two is the wall. Okay, so part one, part two. Okay. So first thing we're going to do is we are assuming that our car chassis here is made of aluminum. And so we're going to go to part one right here. And under material assignment, we're going to change that from structural steel to aluminum alloy. Okay. Okay. So you want to make sure that your car is made of aluminum. Otherwise, it's going to be much stronger, much heavier, but also much stronger than it is. Okay. For the wall, we're not really worried about the wall all too much. It's just there just to make contact. And so we're not going to be measuring like the deformation or the stresses of the wall. And so it doesn't really matter what material we pick for the wall. And so we're just going to keep it as structural steel, the wall. Okay. But you want to make sure you change the car as a material to aluminum alloy. Okay. All right. And one other thing that we're going to do before we jump into meshing is that we're going to mess with the contacts. Okay. And so because these two parts here, they were made in such close proximity, what ANSYS did was that it basically made a bonded support between them. And so if you go under connections and then under contacts, and then you go under contact region, you should see that there is a bonded contact between the car and the wall. Okay. All right, so this will be the first time we're actually going to remove this. So we're going to remove this contact just to make sure that the car can kind of properly make contact with the wall. And then what you're going to see is that the car is actually going to bounce off the wall. So we want to make sure that we capture that behavior. So what we're going to do is we're going to right click on this contact region between the two bodies. and we're just going to delete it. And so we don't need this contact region at all. So let's just get rid of it. Okay. Okay, so that released the contact between the two. Okay, and then now we are good to go. Okay. All right, and so now that we've removed the contacts between the two parts, let's go ahead and move on to meshing. Okay, so meshing here is really important because it's going to be a big part of what determines our results. And so I'm going to go ahead and make two objects here. And so I'm going to make a method object, and I'm going to specify the car. And I'm going to make a sizing object and specify the car as well. Okay. Actually, let's go ahead and make the same things for the wall as well. Actually, I'm just going to make a sizing object. Okay. And so you should have three meshing settings here. So you should have a method for the car. So I'm going to go ahead and rename this car method. Okay. Next, we should have a sizing object for the car. So this will be car sizing. And then finally, we'll have a sizing object for the wall. And so we'll have wall sizing as well. Okay. Okay, so first let's go over the method here. And so we're going to do something that we usually don't do in our other simulations, and that we're going to set the element order to linear. Okay. So normally we don't do this. So normally, if we're running a structural simulation, we're going to use quadratic elements just because they're much more well suited. But remember, when we talked about on Monday, dynamic simulations are a lot more cost intensive, and so they're going to be a lot more expensive to run. And so, there's actually a limitation within ANSYS, and so specifically with explicit dynamics, which actually prevents you from running quadratic elements with explicit dynamics, at least in the academic version.
Dr. Chan.
Yes.
May I ask a question?
Sure.
So this may seem redundant, but just for reassurance and clarity, I see that we have car method and car sizing and then wall sizing. Is there a reason why there isn't a wall method?
Oh, we may have to add one, but the wall, remember, like I mentioned, is we don't really care too much of what's going on with the wall, and so we're just gonna let the defaults handle it for the wall.
Okay, sounds good.
Yeah, the reason I have a wall sizing is that we're gonna make the mesh for the wall very coarse. And so we're going to make the elements very big because, again, we don't really care too much what's happening to the wall. It just kind of has to exist. And so we're going to focus most of our elements, most of our density within the car.
Sounds good.
Okay. And so for the car, we're going to set for linear elements. Okay. Again, that's because of the cost. And so, if you try to run with quadratic elements, and you're welcome to try. Maybe they've changed it in the later versions, but when I first made this activity a few years ago, there was actually a hard stop. So ANSYS actually gives you an error saying that you can't do quadratic elements in explicit dynamics. But they might have updated that in the later version. Wait a second. Yeah, it fails. Okay, yeah. So it looks like that's still an issue. Yeah, so that's kind of the issue. But the main reason is the cost, because they don't want the cost to. So we are going to use linear elements, which is a little bit scary. So, linear elements, we've talked at length about kind of the issues with linear elements. And so you really want to make sure that you have a fine enough mesh for the car in order to capture all of the behavior.
I have a question, sir.
Yes, go ahead.
So does using linear elements make our simulation less accurate?
It does. Yes, it does.
That sounds good.
Yeah, so you need to make up for that. So when you're talking about accuracy of your mesh, you kind of have a couple sliders that you can do. So one thing is that you can change the order of the elements, and so going from linear to quadratic, that's going to make your simulation more accurate. But another way to get accuracy is just to mesh the hell out of it. So just make your element size so small that you have so many elements. And so when you're kind of forced to have a linear element in a situation like this, you really want to make sure that you make your element size small enough to really get an accurate result. And so something like this, when you're forced to use linear elements, I don't think I require it here in this activity, but for a situation like this, you really want to run a mesh convergence test so that you can really show that your mesh is good.
Sounds good. And we're not using quadratic elements because there's an error in ANSYS.
Exactly. Yeah. So ANSYS basically prevents you to kind of limit the costs.
Okay. Sounds good, sir.
Yep. Okay, so actually, let me just go ahead and generate this mesh and let's see what it looks like. And we'll go ahead and modify it from there. Okay. All right, so here we have our mesh. And so you can see, first thing I notice right away is that this wall mesh is way too refined. And so, we definitely don't need a mesh that's that small for the wall, because again, we don't really care about what's happening there. And so what I'm going to do, and I'm going to make this mesh for the wall a lot bigger. And so I think the default size that it's working with is 0.66. And so anything much bigger than 0.66 is going to be fine. Okay. And then for the car, I'm going to refine this mesh a bit. And so again, the default mesh size is 0.6. And so I'm going to try making it 0.4. Okay. So let's go ahead and generate the mesh again. So this is a lot better. And so you can see here that we have a wall mesh that's, that's very coarse, but, again, we don't really care about the wall. But our car mesh is a little bit more refined. Actually, let me try something. So let's see if we can get hexahedral elements on this car. Let me switch this to hex dominant. I'm going to see what happens. I get an error here. Yeah. Okay. Yeah, so if you're able to get hex meshes on the car, that's going to be a big plus. But it would take quite a lot of tinkering because this geometry here is a little bit complicated. So let me go ahead and switch this back to automatic. But feel free to play with it if you're able to get hexes on this car mesh.
What were the sizes again, Professor?
I just kind of spitballed it. So for the wall, I did a size of 2 inches. And then for a car, I did size of 0.4, but that's something that you could play with as well. And actually, I'm looking at the activity specifications. I do say that you can do a mesh convergence test, but it is extra credit. Yeah. And so if you do a mesh convergence test for this one, it is extra. Just be careful because each dynamic simulation, especially as you refine the mesh, is going to be really expensive. So I would recommend, do the mesh convergence test if you have a lot of time on your hands, or maybe you're watching Netflix or something, just run a simulation every half hour or so, and then, get data that way. Okay.
I have a question for that mesh convergence test. Would we have to do it again on the Excel sheet, or this time could we use the feature that has in the app software?
Actually, I haven't. So traditionally, when I've done mesh convergence tests in the past, I just did what you guys have been doing is that you've used Excel. Okay. I've actually haven't used the feature within ANSYS all that much. I've seen a couple students do it. And so if you want to use that one, that's fine as well. So I think what it does is that it automates it for you, right? So it basically runs a few simulations for you. And so if you want to use that, that's perfectly fine because it gives you basically the same data as if you were doing it in Excel. Yeah.
Okay, thank you.
Yep. Okay. All right. So next, let's go ahead and put some constraints on this. And so we're not going to put any loads. Our load is going to be from the motion, but we do have to constrain this just to make sure that we get an appropriate impact. Okay. And so first thing we're going to do is I'm going to put in a fixed support. And this fixed support, I'm going to put on each of the sides of the wall. Okay. So this is important because you want to make sure when you have an impact problem like this, that the surface where your two bodies are impacting, it's able to deform a little bit. Okay. And so you don't want a situation where you apply a fixed support on this face right here, because that's where the car is going to be impacting. Okay. You would think that this would be something that would be okay. But you want to have a little bit of flexibility in the region where you're making contact, just for kind of numerical stability purposes. Otherwise, you could get some weird things in your simulation. Okay? So you have a couple options, and so what you can do is you can add a fixed support that goes around the outside of the wall, which is kind of what I have here, or you could fix it on the back face. That one is perfectly fine too. So. As long as you don't apply the fixed support on the part where the car is contacting the wall, then you should be good. Okay. All right. So that is the wall. Next, let's go ahead and constrain the motion of the car. Okay. And so for this one, I'm going to add a displacement support. Okay. And so if you recall from activity 4. A displacement support lets you basically fix certain components of the deformation, but it leaves some to be free. And so we want to constrain this car so that it doesn't, even though we only have the car chassis and the wall right here, in reality, the car is, is riding along a horizontal road. And so we want to make sure that, whatever motion we capture, the car doesn't like clip into the road, because that would be kind of unrealistic. And so we want to make sure that the car does not kind of move in this Y direction here. Okay. And so to do that, we're going to apply a displacement constraint on the bottom of the car to make sure that our car stays on the ground, basically. Okay, so let's go ahead and add a displacement support. Okay. And let's set the Y component of this displacement support to be 0, because we want the Y component to be fixed. Okay. As for the geometry, I'm going to select the entire bottom edge of the car. Okay. All right, so you might this might take a little while, but you're going to control click on all of these surfaces here. And you should have 8 faces in total. And so you should be able to select all the bottom faces of the car and then fix its Y component. Okay, and that's it for our constraints. And so we're not going to apply any force. We're not going to apply any load. What we're going to do instead is we're going to apply some motion to the car. We're going to give it basically an initial velocity, and then that's going to produce our displacements and our stresses. Okay, but any questions so far on the meshing and the constraints for this solution? Yeah.
What were the faces that you placed on displacement?
Yeah. So for the displacement support, I basically, if you kind of zoom in on the bottom of the car, there's this kind of bottom lip that goes all the way around here. So like kind of where the wheels are and kind of this bottom lip right here. Honestly, I think, applying it to all of them might be overkill. At the very least, I would do all the lips for the wheels, because that's kind of the part that's contacting the ground, or at least the closest part to it. So at the very least, I would have these 4 surfaces. But for me, I just do all 8 all the way around. But at the very least, you should have those 4 surfaces for the displacement.
Would that inhibit it from deforming in the Y direction?
No, so it will still deform in the Y direction. Or I should say the top of the car could still flatten. It's just that these parts on the bottom are kind of fixed onto a rail, but the rest of the car can kind of squish and unsquish like that. It mostly prevents a rigid body motion. That's what it does. All right, any other questions on this here? Okay. All right, so all of that is fairly standard, and so that's why I kind of went fairly quickly on this. Now we're going to get into the newer parts of this simulation. Okay, and so if you'll notice, one thing that's different here in dynamics that we don't have in static analysis is we have this kind of question mark next to analysis settings. Okay, and if at this point you should know that whenever you see a blue question mark in ANSYS, that means there's something that ANSYS wants you to specify there before you run the simulation. Okay. All right, so let's go ahead and click this, and then let's go ahead and see what we need to specify here. Okay. So this menu here is available in static simulations, so you can still modify some analysis settings. There's just some extra stuff in dynamics that you can set. Okay, so after you click on analysis settings there, you should see that there's something in the bottom left here that's highlighted in yellow called end time. Okay. All right, so just like we talked about on Monday, the end time kind of represents the time that you are the last time that you want to basically run your simulation for, okay, or up to, you want to run the simulation up to that amount of time. Okay. And so remember, you want to set this end time such that you kind of capture all of the behavior that you want to. Okay. And so for a car crash, a car crash happens very, very quickly. So we don't have to add a lot of time here. In fact, just for the sake of cost, just to make sure that everyone can get at least a couple simulations done today before we leave, let's set this to be a very small number. So I'm going to set this equal to 0.00075 seconds. right? So about 3/4 of a millisecond. So that's how much time that we're going to be specifying. Okay. And so of course, when you guys are kind of, after we run the first time, you are definitely free to modify this as well. But let's start with this just to make sure everyone can get a simulation done. And honestly, for something like this is enough time to at least see a decent chunk of the results. But again, if this is something that you want to play with, afterwards, definitely feel free. But for now, I'm going to set the end time to be 7.5 times 10 to the minus 4 seconds. Okay. Okay. But of course, if you're simulating something that's going to take longer than this, you want to make sure that you adjust your end time accordingly. But for now, we're just going to set that to be that. Okay. All right, so that's the most important thing that we have to set, and so we have to make sure that we set that proper end time. Okay. If you remember from Monday, the other thing that's important for dynamic simulations is the time step size, right? Or in other words, the amount of time that's in between your frames of your animation. And so the good thing is that, by default, ANSYS will control your time step size for you. So if you look under the analysis settings, there's quite a few settings here with regards to the time step size, okay? And you can see that most of those are program controlled because ANSYS can change that dynamically, okay? And so when you're first kind of starting out, I would say go ahead and keep that. So kind of let ANSYS kind of decide the time step size for you. Because ANSYS, it is kind of tracking several metrics throughout your dynamic simulation. So it'll set something nice. But if you did want to change this, if you did want to basically set your own time step size, this is kind of where you would do. But for now, we're just going to let kind of ANSYS do its thing. The only thing it wanted us to do was to, specify what the end time was, which is what we just did. Okay. Any questions on this so far? Okay, so one more thing that we're going to do here is we're going to specify the initial conditions. Okay. And so this is how we're going to add motion into this system. And so basically the motion that we're going to add is we're going to make this car and we're going to slam it against the wall. So we basically need to give it a velocity in the X direction. Okay. And so let's right click on initial conditions and we'll go to insert. And the initial condition that we're going to add here is a velocity. Okay, so let's go ahead and click on velocity. All right, and then what we're going to do here is we need to specify, first of all, which body or which part of the geometry that we want to specify the initial conditions on. And then we need to give it a value for the velocity as well. All right, and so make sure that you're on volume selector mode and you're going to select the entire car just like that. Okay, so go ahead and click apply for the geometry. Okay. And then let's go ahead and give it a velocity in the X direction. And so the way we're going to do that, just like we usually do for our modes, we're going to change the defined by, and so we're going to change it to defined by the components. Okay. And then we're going to give it a velocity in the X direction. Okay. Okay, so let's, go ahead.
Sorry, I have a quick question. What if we were to use vector and then would click on the X arrow? Would that be the same thing?
Yeah, that's the same thing. And so if you want to do vector and you click on this X direction here. Fine. Yeah, actually, usually there's a vector that kind of shows up, and then you can kind of click it in that way. So if you're more familiar with that, that's fine. But I usually like components because this is a lot more exact because it's because then you can specify exactly the X, Y, and Z components.
Yeah, it's just out of curiosity.
Yeah, both will work just fine. It's up to kind of personal preference. Okay. All right, so for the X component of velocity, for now, it doesn't really matter what we put for this. So we can kind of put any kind of any value here. The only thing you want to make sure is that you're going in the negative X direction because you want to make sure the car hits the wall. It doesn't run away. Okay. All right, so for the X component, let's say that we do a velocity, let's do -600 inches per second. Okay. right, so fairly large, but it should give us some good results. Okay, any questions on the velocity condition here? So feel free to set any velocity magnitude. I mean, you're going to be playing with it anyway throughout the class today. But just set a value for it now, just so that we can kind of run an initial simulation. Okay, so we're just about ready. And so we have everything that we need to. So the last thing that we're going to do here is we're going to specify our output fields. Okay, so just like usual, we're going to set the total deformation. We're going to look at the equivalent stress. We're going to look, and we're also going to add equivalent strength. Okay, so this one's a little bit new, but you'll kind of see why we do this in a second. Okay, so you should have 3 result fields. So you should have the total deformation, the equivalent stress, and the equivalent strain. Okay, so now that we're all set to go, we can go ahead and hit solve. Okay, all right, and so now this part here is going to take a little bit of time. And if you want to check the progress of your simulation, as always, you can kind of check the bottom left corner of the screen here.
When doing the meshing part, when we use method, why can't we use quadratic the wall? And yet in kinds of one of the wall.
Yeah, so for the mesh, it basically checks the mesh order all around. So even though the car is the only one in motion, technically the wall is still part of the dynamic simulation too. And so it basically alters kind of the governing equations that go into the computer. And so even if the wall is quadratic, and even if the wall is not that is fairly stationary, it still affects how the equations are computed overall. Yeah. Okay. So the simulation is actually almost done. So that's actually pretty fast. It's faster than usual. But I do want to show you something. And so while the simulation is running, and actually you can look at it after as well, you can click on solution information here. Okay. And then what we're going to do is we're going to click on this solution output, and I'm going to look at energy summary. Okay. And so this is a really cool plot right here, because what this shows you is kind of the overall kind of sense of energy within the system. Okay. And so I want you to kind of take a look at this, because initially when the simulation first starts, okay, you can see here that most of our energy is in kinetic energy. Okay. And the reason for that is because all the energy in the system is being provided by our initial conditions, and that's being given to the motion of the car. So we're giving the car a lot of motion, and so that's where that energy comes from. All right, so right after the start of the simulation, the car is going to make contact with the wall. And then as the car makes contact with the wall, what's going to happen is that the car is going to start to crumple up together. And so the car is basically going to start straining and deforming. Okay? And so basically what's happening there is that your kinetic energy is being converted to internal energy. Okay? So the way it kind of, the way ANSYS kind of, quantifies, energy or deformation energy is by internal energy. Okay? And so as the car makes contact, the kinetic energy goes down. Meanwhile, the internal energy here goes up because the car is deforming. Okay? We can see that in the animation. So now that the simulation is done, so let me go ahead and view the results. So let's look at the stress actually. Okay, so if you want to see the animation of your car crash, you can click on any of the output fields here. So I click on equivalent stress. Okay.
Dr. Chan, I have a question.
Sure.
So
go ahead, Ivan.
When the car is how do I word this? When the car is getting collapsed in the X direction, does the internal energy get converted into heat, or where does the internal energy go?
No, that's a really good question. So right now, essentially what we have here is a linear elastic model. And so there's no mechanism right now for any of that energy to actually get dissipated. And so, the car is going to hit the wall. It's going to crumple a little bit, but there's nowhere for that energy to go. And in fact, speaking of, before spring break, if you remember, we talked about nonlinearities. We haven't introduced any nonlinearities into the system at all either. And so basically, this car is on this kind of linear stress strain curve. And so actually what happens if you kind of play the animation here, you can see that the car hits the wall. You can see it's deforming a little bit, but then it bounces back to its initial configuration right away because we have that kind of linear elastic model. So there's no way for that energy to be dissipated. And so actually, if you look at the energy summary, you kind of see that exact same thing. So the car hits, okay? Most of the kinetic energy gets converted to internal energy.
Yes. I understand that.
Yeah, so for most situations, most realistic situations, it would kind of stop right here, because then that internal energy would either get converted to heat, or it would kind of buckle and it would permanently deform. You'd have plastic deformation, things like that. But because we are working with the linear elastic model, you can see that the car basically acts like a spring, and so it kind of springs back, and so the internal energy goes back down, and then the kinetic energy comes back.
Oh, that's very interesting.
Yeah, and you have kind of these vibrations that are happening out here, and so
I see.
and the frequency of these vibrations, it's on the mass and the stiffness and things like that. So this is not I think this activity is kind of fun to do, but it's very unrealistic because there's a lot of limitations that we're kind of working with.
Yeah, there's a lot of constraints being applied. Thank you, sir.
Yeah, mostly due to cost, and so
that's very interesting. That's very interesting. You mentioned the spring analogy. It always goes back to springs.
It does. Yeah. No, it's a thing.
Sounds good, sir. If someone has posted a question.
Yes, I see. So a couple of questions in the chat. So in the PDF, I said to use a velocity of minus 150 meters per second. So yeah, so that is very extreme. And so 150 meters per second, I think that's the speed of a bullet or something like that. And so I think I did that in the specs just to kind of exaggerate kind of the deformation. And so you can kind of kill this, and so you can kind of add more velocity if you want, and you can kind of see the car deform a lot more. So I did kind of something extreme in the PDF, but it's something you're going to be playing with anyway. So it didn't really matter what the initial velocity is. Yeah. All right, question, Professor, can we change the car's distance from the wall by ANSYS? Yes, and so if you open up the CAD software, so you open up Space Claim. What you could do is you could move this car away from the wall as well. And so that's something you can do. Yeah. And so right now, the way it's set is that this is basically moments right before the car hits the wall, or actually the car is actually making contact with the wall. And so that's why it's there. But you can move it farther away if you want. Yeah. Question.
The animation setting you were showing, the bottom that shows the graph. How do if it's not there?
Yeah, so if this is not there, then what you can do is you can go up to layout right here in the top right, under home. And so under home up top, and then you go to the top right here from layout, and then you just click on reset and layout. And that should bring everything up. Yep. Yeah, so definitely play around with it a bit. So try to run a couple simulations, change the velocity. Actually, let me go ahead and change this. Let's do something really extreme. So let's add a 0 here. Okay. Let's go ahead and run the simulation. And I guess while that's running, let me go through a couple more things in the PDF, just because that's basically the activity there. And so let's go ahead and go over kind of what you have to do for the rest of the class today, because it's mostly going to be on. Okay, so we've basically done up to problem 4 of the analysis. And so after this, there's only a couple more parts that you have to do. And so the first problem that you have to do here is problem 5. And what I want you to do for this part is I want you to find the maximum velocity for the car. Okay. And so, a common theme in this class is that, we like to talk about a lot of, is this part going to fail under these given conditions? Okay. And so for this problem here, I want you to kind of tinker with that initial velocity of the car until you get a equivalent stress of around 55 megapascal. It doesn't have to be exactly 55. And so if you're somewhere between 50 and 60, that's fine with me. So don't don't kill yourself running, dozens of these simulations to get exactly 55. So as long as you're in the ballpark of 50 to 60, that's fine with me. But I want you to find the approximate velocity of the car that you can ram it into this wall and still have it survive, basically. Okay. So that's problem 5. Okay. Problem 6, I want you to basically repeat problem 5, but I want you to change the material properties of the car to plastic. Okay. And so if you go back to the kind of very beginning of the activity today and you go under general materials, you should see some plastics that are available in there. So I think the one that I use for this one is polyethylene. And so you can do that and you can repeat that analysis. But because we are working with quite a condensed schedule, and so we are basically doing four activities in 6 weeks. I don't want to overload you guys with work. So problem 6 here is going to be optional. Okay. I think it's fun. I think it's really cool just to kind of change the material and see what's there. But I don't want you guys spending too much time on this because we do have the final project coming up, and next week we're actually doing another activity. So I don't want you working on this too long.
I have a question, sir.
Yeah.
Thanks for taking into consideration the time left in the semester. So having said that problem 6 is optional, does that mean that it's not worth any points? Does that imply that
this one is not worth any points because it's basically just a repeat of problem 5, so it's not anything new. The mesh convergence test, if you do that one's worth extra point because that's actually extra, that's newer stuff. Problem 6 is go ahead.
When we submit our homework submission, what would you like for that section for problem 6?
I mean, you can just label it as problem 6 on the homework. Okay. I mean, I'll just kind of glance over it.
Sounds good.
Okay. And then after that is just the usual. At the very end, you're just summarizing your findings. And so, we're doing most of the activity today, and I'm leaving one part out just because we're working on a condensed schedule. But that's basically the activity. Okay. All right. Any questions on any of this? Okay. All right. So once you guys, so we do have about half an hour left of class, about 35 more minutes. And so once you guys keep working on that, you can start working on problem 5 here. Let's see how my simulation did. Okay, so yeah, this is the reason why I set the velocity to be really high. So you can kind of see the car like really, it's really kind of jiggling there. It looks kind of funny, but again, this is not super realistic because we've made basically a ton of assumptions, a ton of shortcuts just for the sake of cost. And so, in reality, you don't see this, the car just ends up just crumpling in on itself, but it's kind of fun just to see kind of what happens. And so you see a little bit of kind of the linear elasticity, but also a little bit of vibration that we talked about on Monday as well. Oh, actually, one more thing that I want to kind of discuss before we go. Okay. So I had you guys kind of view the total deformation field because that's kind of what we normally do. Okay. But if you'll notice from the total deformation field, it looks a little bit weird, right? And so if I kind of stop this, right, you'll see here that the car's deformation right now is all red. Okay. Which is not really that helpful because remember, we run finite element simulations so that we can see kind of finer gradients or finer patterns in our structure. And so the fact that this deformation is all red, it kind of looks a little bit strange, right? The reason for that is because of how ANSYS measures deformation. And so, if I play the animation, this motion is a little bit exaggerated, but the way ANSYS measures deformation is that it takes the starting location of each node in the mesh minus the ending location, and that gives you your deformation. Okay? And so deformation actually is not that useful in dynamic simulations because things are moving a lot in dynamics, you're going to get deformations that are very large because the part just naturally moved far away from its initial condition. Okay? And so if you want a better kind of indicator for how the car is actually deforming and actually changing shape, strain is actually going to give you a much better result than the deformation. Okay? And so that's why, the deformation looks a little bit strange. If you play the animation, the whole car kind of changes colors together, basically. And so you don't see kind of finer gradients, except for this kind of weird kind of jiggle thing that's going up on the top here. Right? And so for this activity, I would recommend that you look at strain rather than deformation. Stress as well. Right, and in order to get the, again, in order to get the stress in megapascal, you might have to change these units, and so, you know, you can do that as well. Okay, any final questions on this?
I do have a question.
Sure.
Is lecture over?
Yeah, it's over.
Okay.
Yeah, so I'll stick around here. I'll stick around here for the next half hour. And so if you have questions on the activity or if you're having issues, I'll help out for the next half hour, but you know, that's basically it. And so I'm not going to cover any new content from here on out. And so you are free to go.
Sounds good, sir. Have a good night, sir.
Thanks, you too.
Thank you, sir.
There are questions here? Yeah. Okay. Information distribution. Yes. So I still want to see, some shots of the definition, but I'm just kind of explaining why it is. Yes. Yeah, so I mean, obviously the animation, just showing kind of this screenshot of what you see. Yes. You don't have to, Good. Yeah. Good.
For the mesh conversion test.
Yep.
Would you still recommend minimum 10 points or 10?
For this one, it's going to be tough to do 10. So I would say try to do 4 or 5.
Are you gonna get extra grades, extra points because of that?
Yep. For what?
A mesh conversion.
Yeah. I'll give you 10 extra points on the activity if you do mesh convergence tests. Yeah.
Yeah, I've been doing a couple points and
It takes a while. Yeah, that's why it's extra, because it takes a long time. These dynamic simulations are no joke, and you know, you can see. So we did a ton of simplifications today. We use linear elements. We use, you know, linear elasticity, no nonlinearities, and it still takes forever to run a simulation. Especially when you push it to those really high element counts. Like that's something you just, you know, you set it, you go cook yourself dinner, and then you come back and hope that it's done.
mesh was already taking longer. Still.
That's kind of how it is. Yeah.
So when doing the mesh conversion test, change the mesh size only for the car.
Only for the car.
Only for the car.
Yeah. Yeah. Oh, yes, usually I just.
So when we do it in our laptop, this do this to shut it and reopen it again and start saving. This goes into a read-only mode.
Oh, really?
Why is that?
Oh, I have no idea. Never done it. It's usually I use it on. I just make sure before, just make sure you save.
Just save it.
Oh, wow. Oh, yeah, much. Yeah, much.
That's the initial. It's just.
Yep.
And sure one way. Play, then it changes.
Yeah. Yes, because what you're doing is just kind of the final. Yeah, so you're right here. Yeah, you're right. So the actual boosters.
Deformation doesn't change. The deformation.
Yeah, because
because the end is gonna be.
exactly, because the car bounces off. That's why you see the max deformation. The stress, the max stress is extended.
Professor,
Yes.
I have a quick question.
Sure.
The time history is not showing up on my graph window. Is there any way I can bring it up?
You mean the this thing on the bottom here?
Yeah, that one.
Yeah, if you you can try resetting your layout. So go to home right here. And then click on here and then reset the layout. Does that bring up the time history on the bottom?
Hold on a minute. You just close everything.
Try after you reset it, try clicking on another result here. So click reset and then click on, maybe a different result. That's not there.
All right, thank you.
Does it work?
I forgot to save it. It cleaned everything.
Oh no! Oh shoot!
I have to start over.
Oh,
Oh shoot.
yeah. This at least this time there's not that much settings to do. It's not like activity 4 where there's a lot of modifications though. Yeah, you should be able to get it up back up in like 10 minutes.
Yeah, I'll do that.
Sure. Yeah, that's what it's. Oh, yeah, I mean, there's gonna be some discrepancies just because you're, I'm guessing you guys use the same one. Yeah. Yeah, so because there's gonna be some discrepancies in terms of how. Because you saw the car kind of jiggles. Yeah. Jiggles. There's a little bit of randomness in terms of how deformation is going to get distributed throughout the art. Part of that depends on the mesh. Because we're using linear models, there are kind of the comparable. Even if you use the same mesh settings, there's some randomness in how actual elements. A little bit of kind of both. Yeah.
Hello, Professor.
Hi.
I'm sorry I skipped like half of the class because I was breaking my fast, so that's why I'm the last one here. I'm
Okay,
sorry
no,
about
no
it.
problem. I mean, people are still here in the classroom too.
Yeah. But anyway, Professor, thank you very much.
Okay.
Awesome. But then it's not going to do that. We have to nail it.
Thanks, you too.
I opened the project that I did. Look at this was the separation.
Yeah.
Yeah.
So when you change the velocity, you have to put the end.
You don't have to.
What was later?
I think it's.
Oh, okay. Oh, okay, if you, yeah, if you increase it significantly, then it may not have, let's look at this, open on solution. Yeah, so I'm looking at this one, to see if it had looks like it's contact. And it vibrates. It looks like it's like a machine. Could be, settings. By increasing it, it looks like it's, I think basically what it's saying is that you have some result that is specified for this time for the simulation. It's like it's 0.00075. And so I think it's just made on this sheet. That should. I'll stick around. Let me know.
See you.
Yeah, see you next week. You too.
You first,